This lecture is going to be over sections sections 16.3 and 16.4. We're going to be looking at internal combustion engines and refrigerators. So, an idealized model of the thermodynamic processes that take place in a gasoline engine is called the Otto cycle. The theoretical efficiency of the Otto cycle is about 50%. If you look at the efficiencies of real gasoline engines, you're typically looking at around 20%. In 16.4, we're going to see that a refrigerator is going to act differently from the heat engine that we looked at earlier, where it takes heat, Q sub C, from a cold place and has an input of work and then discards the heat in a warmer place. So the performance coefficient, K, of a refrigerator is going to be defined as K is equal to Q sub C divided by W, or the amount of work. And then if we look at the amount of work here, where work is going to be the difference between Q sub H and Q sub C, we will get our performance coefficient. So that'll be the second half of this lecture. All right. So for internal combustion engines, these are going to be used in a lot of different types of machinery, automobiles especially. So we can see the diagram here of an internal combustion engine. So we've got our intake stroke where the piston moves down, causes a vacuum, and what happens is your intake valve starts to open. And your gasoline air mixture enters into the cylinder from that intake valve. So it swings around, comes around to the compression stroke, and then the intake valve closes. The mixture is compressed as the piston moves up because the piston is going to be pushing against that mixture. As it pushes up and your spark plug fires, you're going to see the mixture ignite. When it ignites, you're going to see the power stroke. So as the power stroke happens, you see the gas expand and it pushes that down. And then as it comes around, you've got the exhaust where this valve opens up and the gas is, or the whatever the remaining material is here, expels the exhaust, and it's now ready for the next intake stroke. And then you just repeat that cycle as you go along. So let's take a look here. This is going to be a diagram of the Otto cycle. So we're going to assume that the gasoline air mixture behaves as an ideal gas. And again, this is going to be an approximation. So at point A, right here, we're going to see that the mixture has entered the cylinder. The mixture is then compressed adiabatically, which means no heat moves in or out, and moves along this particular line. This is going to be your compression stroke. Then boom, it gets ignited. And then you see the heat of combustion is added to the system by the burning gasoline. And then the power stroke is going to be going from here to here, from C to D. And then the gas is cooled to the temperature of the outside air as it goes through here and then is released. The same air doesn't enter the cycle again, but it's an equivalent amount. You know, it almost acts as if you could clean the air somehow and have it come back, it would act the same way. So this is going to be referred to as the Otto cycle. Again, it's something that's highly idealized. The diesel engine is going to be similar to the gasoline engine, but it has a power stroke that operates at a nearly constant pressure, and is sometimes called the diesel cycle. The most important difference between the Otto and the diesel cycles is that at the beginning of the diesel compression stroke, the cylinder contains air but no fuel. A little before the beginning of the power stroke, the injectors start to inject fuel directly into the cylinder, just fast enough to keep the pressure approximately constant during the first part of the power stroke. Because of the high temperature developed during the adiabatic compression, the fuel ignites spontaneously. In other words, no spark plugs are needed. You don't need anything to ignite it. I thought that was kind of cool. So now let's take a look here at 16.4. Again, we're going to look at sort of a heat engine in reverse, and that's going to be a refrigerator. Because we, as humans, have reasons for why we need refrigeration. It helps to deter bacteria growth. It helps keep certain molecules stable. You'll know with the certain COVID incident that we have going around right now, the vaccines that are being developed have to be kept at a particular cold temperature. At least some of them do. And that's in order to keep things stable in order to be able to deliver it. So there are reasons why we need refrigeration. For a heat engine, it's taking heat from a hot place and giving it off in a colder place. Refrigerators are going to do the reverse. It's going to take heat from a cold place inside the refrigerator, because we want to keep things cold, and gives it off to a warmer place, usually the air in the room where the refrigerator is located. So a heat engine is going to have a net output of mechanical work, and refrigerator requires a net input of mechanical work. So we're going to take a look at this particular diagram here. QC is going to be considered positive for a refrigerator, but both this and this are going to be considered negative. So the absolute value of the work is going to be minus W, and then the absolute value of the heat released into the hot reservoir is going to be minus QH. So we've got a refrigerator here. We've got the compartment in which we want to keep the cold temperature. So we're taking heat out of that. We're having some work applied to it, and we're releasing all of that heat into an area that we don't really care is whether or not it's refrigerated. So for a cyclic process, that means the internal energy here is going to, the change in the internal energy is going to be 0. And so therefore, Q minus 0 is going to be equal, Q minus W is going to be equal to 0. And given the sign conventions that we had up there at the top, this is what we're going to come up with. Because both this and this are negative, what we end up discovering here is that the absolute value of this is going to be equal to the absolute value of this plus the absolute value of this. The way I kind of think of it, and what was discussed in the previous section, is if you consider these to be pipes, the size of this plus the size of this pipe, if you look at it here, it's going to end up being the size of this pipe. The same thing works in reverse for the heat engine. Now, if we are interested in the efficiency here, we've developed something here called the performance coefficient, K. K has no units, just like the thermal efficiency that we had before, the heat efficiency. We're going to have Q sub C divided by W. Again, we put in the amount of heat that is being pushed out and the amount of heat that it's taking in, and then we come up with a ratio. So the principles are going to be of refrigeration are exemplified here. You've got inside the refrigerator, you've got the evaporator here. It's taking in some energy. You've got a compressor here, which is going to take that low pressure, make it a high pressure. It's going to be hot out here, and then it's going to lose its heat. As you go over here to the condenser, you've got the expansion valve. So as this thing expands, that's going to get colder, and then the cycle continues. Now, depending on the make, model, whatever it is of the refrigerator, all of these coils are going to be in different spots. And that's what this diagram is going to show you regarding mechanical refrigeration cycle. You got the evaporator coils inside, you've got the condenser coils outside, got your compressor here, and this, the electricity is going to supply the work that we need. So refrigeration, an air conditioner operates on exactly the same principle. In this case, the refrigeration box becomes a room or an entire building. The evaporator coils are inside, the condenser is outside, and the fans circulating the air through these components. You can see it right here. If you're inside a building, then you've got the coils in here where you've got the warmth coming in, you're wanting to get rid of it, blowing the cold air out. So you got the warmth coming in, then this thing circulates, going through condenser. Then you've got it flowing over here where the fan is blowing the hot air out, and then you will have this go through the expansion valve, and then the process continues to repeat. In large installations, the condenser coils are often cooled by water. For air conditioners, the quantities of the greatest practical importance are the rate of the heat removal, the heat current H from the region being cooled, and the power input to the compressor. So if heat Q sub C is removed in time T, then the heat current is going to be the heat from the cold reservoir divided by time. And then if you express power in terms of the amount of work divided by time, then you can come up with your coefficient here being H divided by P. Now, if you have an interest, sometimes you might hear of units that blow a certain amount of ton or something like that. You know, a 3-ton unit, a 4-ton unit, or whatnot. A ton usually refers to about 12,000 BTUs per hour. Depending on how big of a house that you might have, usually you're looking for about an air conditioner that will process about 1 ton per 500 square feet. And if you use that ratio, then it gives you an idea as to what kind of unit you're going to need in order to be able to make sure that your house is comfortable. You've got some discussion here regarding the energy efficiency ratio. That would be good to look at. Variation on themes, the heat pump, it's used to heat buildings by cooling the outside. It functions like a refrigerator turned inside out. So the evaporator coils are outside as opposed to inside, where they take heat from cold air or water, and the condenser coils are inside where they give off the heat. These are usually designed so they can be run as air conditioners in the summer. In this particular model, a heat pump has no extra efficiency over a standard air conditioner. But the bottom line here is some work is always needed to transfer heat from a colder object to a hotter object. Heat flows spontaneously from hot to cold, and so to reverse this is going to take work.